We've been talking about the laws of thermodynamics, and so far we've defined two of them, the first law and the second law. There's two more laws that we need to go over before we can move on. Today we're going to start by looking at the third law of thermodynamics. Real quick, let's review the first and second. The first law of thermodynamics, remember, is the conservation of energy. Energy cannot be created or destroyed. It only changes forms. An example of this is the fuel being used to run a car. This fuel is burned, so the energy that it has, these are all different little molecules, the energy in these molecules is broken and released in the form of heat that allows a car to drive forward. So the chemical energy is being converted into kinetic energy. So that first law is conservation of energy. So what about this third law here? The first law defines that energy can't be created or destroyed. The second law defines how energy is arranged is going to become more chaotic over time. Well, this third law puts those two together. The third law of thermodynamics says that the energy of a system is going to be the most orderly when all of the random motion of particles has stopped. What does that look like? Remember, we learned that temperature is really all about the motion of these molecules that are so tiny, there's no way for us to see them with our bare eye. So, the third law of thermodynamics defines a point called absolute zero. This is when it cannot get any colder. The temperature cannot get lower than absolute zero. So our temperature scales of Celsius and Fahrenheit, neither of those are absolute temperature scales. Celsius, 0 degrees Celsius, is the freezing point of water. Absolute zero is negative 273 degrees Celsius. Now think about that. In the Celsius scale, room temperature is around 20 degrees and water freezes at 0. So think about the difference between a comfortable room temperature and then think about how cold it would be to hold just regular ice in your hand. Think of how cold that is. Now, absolute zero is more than 15 times as cold as that melting ice in your hand. That is a huge difference in temperature. So, the third law really states that a system with no molecular motion, so when all of those particles that are always whizzing around everywhere have finally come to a stop, then we will have the lowest possible temperature. We can't get colder than that. And, remember the second law, entropy. Where does entropy play into this? Our entropy will be the lowest it possibly can be. So at absolute zero, when we've removed as much of the heat energy that we can, as much of the extra energy moving around this system, we will also have reduced entropy to the smallest it can possibly be. Now, sometimes the third law is worded in a way that says it is impossible to get to a point where there is no molecular motion and entropy is zero. We'll be able to see why that is when we come back to looking at how a refrigerator works. It is impossible to get to a temperature this low because the only way to do it is to remove energy from the system. So, our little diagram here shows that 300 degrees Kelvin, Kelvin is our absolute scale, where 0 degrees Kelvin is the absolute zero, it is the lowest possible temperature. 300 degrees Kelvin, our molecules might be moving with this velocity, this speed, this amount of motion. 200 degrees, 100 degrees colder, might be moving with this, a little less. 100 degrees, they're moving just a little bit, and at zero, they're not moving at all. So really, at absolute zero, we have no molecular motion. Why does this matter? Well, the third law, defining absolute zero, is really helpful for doing things like using the ideal gas law in chemistry and physics. It's having an understanding of that, on how gases are going to behave, that we're able to use to relate things mathematically so that we can make predictions and inventions that move heat around. In order to be able to do that, all of our calculations need a scale that uses absolute zero for the zero value. In other words, in order to make inventions that move heat around the right way and not make stupid mathematical mistakes, our temperature scale, when it says 0 degrees, it needs to mean exactly 0. The zeroth law of thermodynamics. Now, before I show you this law, let's keep in mind 1, 2, and 3, each one kind of gets a little more complex to define. So if we go the other direction, the zeroth law should seem really simple and obvious. And it really does. The zeroth law is thermal equilibrium. It states that if a system is in thermal equilibrium with two other systems, those systems will be in thermal equilibrium with each other. That's a little weird when it's worded that way. But what it really means is that if A and B are at the same temperature, so we'll put a little equal sign between them, and B and C are at the same temperature, then no matter what scale we use, A and C will also be at the same temperature. That seems really obvious. Well, it is. It's basic, it's a really basic idea, but what it does define is that temperature is in fact a measurement system that we can use to measure thermal equilibrium. And it defines that at certain equilibrium states, the temperature is going to be the same. So if I'm using a thermometer and I'm putting it in, let's say C is a solution of water at 100 degrees, if I put it in this water and this thermometer doesn't read 100 degrees, well then I know there's something wrong with the thermometer. If I use 2 or 3 thermometers and check the temperature in this, these 3 should all equal each other. And if they don't, then I know there's something wrong with that. So one, it gives me a way to check if my thermometers are right or not, because they're not going to measure something different. They should all be measuring the exact same temperature. But it also defines that if there is a difference in temperature, we're going to have heat flow. So it's not just if there's a difference in energy. It's if there's a difference in temperature, which is a very specific type of energy. Now, where might this be useful to think about? Well, we can actually think about it in terms of global warming. We have two very different systems at play when we think of global warming. We have the Earth, and we have the Sun, which is much larger than the Earth. The Sun is much hotter than the Earth as well. We do not have thermal equilibrium between these two systems. So the energy pouring out from the Sun hits the Earth. Now, over time, the Earth is going to release that energy into outer space, just like the Sun does. But how much energy is it going to release at a time? Well, normally it would release this much energy. But the idea behind global warming is that, well, if we release certain gases into the atmosphere, what we really do is we insulate the planet, just like putting extra insulation in the walls of your house. When we do that, it makes it harder for this energy to get out, and so less energy escapes. We're still getting the same amount of energy from the Sun, but we're going to get into a thermal equilibrium with the space around us. We're going to release a certain amount of energy based on how insulated our atmosphere is. So this zeroth law of thermodynamics really helps us look at things like heat transfer, when it's going to happen, when it's not going to happen, and when it's going to stop. So it allows scientists to make predictions about what will the global temperature be if we put more insulation in our atmosphere. Just like a scientist or an engineer could come into your house and tell you if in the dead of winter you decide, screw it, we're going to open all the windows. Well, it'd be a lot easier for that heat to escape your house. Using the zeroth law of thermodynamics, we would be able to make predictions about what temperature is the inside of your house going to reach, even with your heating system blowing at maximum capacity. So even though it seems really simple, And often the really simple laws end up getting the most complicated words because we're trying to put this basic fundamental idea on paper. It is actually extremely important. So the zeroth law of thermodynamics is really thermal equilibrium.